Right. So in this presentation, I'll give you an overview of PGX.D aDFS. That is the work that we presented recently in using Usenix ADC. So of course you can find all the details in the paper. So here I'll just give you a high-level overview of what we did for this work. And of course, this aDFS system is essentially a pattern matching graph querying algorithm that is used in Oracle Labs PGX distributed. Right. So, I mean, we are all very familiar with graph queries, but still, let me give you essentially the motivation that we present in the paper. So, I mean, why is graph querying like a different problem, for instance, than graph mining that they are doing nowadays in academia? So first, you need in any query to support any user expression that the user might ask. So this is completely dynamic, right? So in graph queries, you're doing homomorphic matching and you return all result permutations. So in academic style of graph mining papers, you do like isomorphism and you remove the permutation of queries. Of course, we have a limited locality in graph workloads, it's as well known as it gets, right? And especially in a distributed system. And of course, we have intermediate result explosion. So on Twitter graph, on the classic one, for one hop, you get the complete graph, 1.5 billion results. And as you go 2 hops away, you already have extreme explosion, right? So you have a 9.3 trillion matches. So, I mean, what we claim in the paper and what actually happens in practice is that you need a distributed solution that is flexible to be able to support any user projection and any user query, right? And can handle the scale of this style of workloads with trillions of matches and potentially intermediate results of final matches, right? And as a spoiler, with PGX.D aDFS, for instance, we can run this query with 8 machines in approximately 20 minutes. That results in something like 8 billion matches per second. And we do this with only something like 1 or 2 gigabytes of runtime memory per machine. Right. Let's see quickly how do we achieve this in aDFS in PGX.D. So aDFS is built on top of 2 principles. So first, it works with asynchronous operations. So this means that the worker threads operate independently. So essentially, worker threads focus on parts of the query that has work to be done. And then workers buffer and forget remote traversal. So whenever you have an intermediate result that is targeting a remote machine, the worker simply puts this in a buffer and forgets about it until the buffer is. So essentially, workers do not block due to remote communication, or like almost never block, let's say. And then we have almost the depth-first traversal, which means that the whole runtime is aiming at taking intermediate results and bringing them to make them final results. So this allows us also to do fine-grained flow control in order to be able to control the memory consumption of the runtime. Now, why do you want to have these principles in your runtime? Is quite, I would say, obvious, but still, let's take a look at an example. We have here a tiny graph, like with 5 million edges, and we count cycles of different, like a hop lengths in this tiny graph. So we are comparing here our aDFS runtime with eager depth-first completion compared to like a fully BFS. Like a runtime that is expanding all intermediate results across hops. So what you see here is that for 4 hop cycles, the memory on both runtimes is pretty much the same. 5 hop cycles already BFS is exploding, and then for 6 hop cycles, you already have on this tiny graph like more than 6 terabytes of intermediate results in total from the BFS runtime, and the query cannot be completed. While for aDFS, we have essentially fixed runtime memory. So what we claim here is that it's essential to have in-memory distributed execution with controllable memory usage. So let's see how do we achieve this in aDFS in more detail. So I will not have the time to explain how we go from a PGPL query, from a graph query to the execution plan, but what is important for the next slide is that we take the query that here is a simple chain of A, B, C, D, and we translate this query to stages where on every stage, essentially, we know how to move to the next stage, and also every stage is simply matching a single vertex. So a stage matches the vertex and knows how to move forward to the next vertex, essentially. So let's see now how the asynchronous DFS, BFS traversals work with this stage-based model on this same example of A, B, C, D. So, I mean, we see this like an execution, like an activity diagram from the point of view of a vertex. So a vertex starts by massing state 0, so A on a vertex, and then of course it wants to move to stage 1, to B. So within a machine, we can actually do like a complete depth first search. So we can actually operate, if needed, with a single intermediate result at a time per worker, right? So here you see that you do full DFS on the query, and you produce your result. Now, when this same thread, like on a different path, hits a remote edge, as in this example, so this C is targeting machine 1. What it does, it buffers actually this intermediate result in a message buffer, and then it can continue execution with like other edges and other matches, right? So as you saw in the animation, when the buffer becomes full, this thread tries to send the message to the target machine, and now this is the only way that this sending can be blocked. So if a flow control tells you that you can send this message, you are within memory limits in the system, then this sending is happening. Otherwise, if the flow control that keeps track of essentially memory consumption tells you that you would violate the memory requirements for this query, this message buffer is put on the side, and then this thread is doing some other local work, for example, receiving messages or completing other paths. Of course, later this sending is retried, and eventually the sending happens and the query completes. So essentially, I mean, we can prove that the protocol is deadlock free, so it always terminates. Right. Of course, I mean, these messages, these buffers that are sent to those remote machines are picked up by other threads, and they are extended either with depth first, or if messaging is needed, with messaging as well. Right, and the main question, one of the main questions that we answered in this paper is that whether this depth first, like strict depth first, is the best approach that you can do, and the answer that we give in the paper is not really. It is beneficial sometimes to have some within the machine, like BUSD limited breadth first search, because it gives you locality, it gives you like better word parallelization and things like that, as we described in the paper.
Vasileios, you have 3 more minutes.
Yes, I think I'm on time. Thanks. Right, so I'll give you only one like a figure with experiments. So we are comparing here like aDFS with Apache Spark Graph Frames, Neo4j Community Edition, MongoDB, and PostgreSQL on like 4 different graphs of increasing size. So live journal, random uniform random graph with 1 billion edges, Twitter graph, and then web graph UK. And what we are like, query 1 is a simple cycle ABA, and then query 2 is like unconstrained ABC, like 2 hops, like a query. So as you can see, with the live journal, this a small graph, you actually get like all engines being able to complete the query. Going to this random 1 billion, like a uniform graph, you already see that some engines have trouble to finish within 8 hours this query. And then going for the real large scale, you can really see that none of the other engines is really able to handle the scale of these queries, right? While PGX.D is executing those with 1 GB runtime memory per machine. Right, so essentially what we claim in the paper is that only the aDFS can handle this scale. Right, to conclude, so we have aDFS, that is a fast, scalable, distributed graph querying engine. It provides flexible PGL querying, combines BFS with DFS, and limits max memory uses. Also in the paper, you can find experiments with the LDBC graph and queries, of course, and a very thorough comparison against like a graph mining system as well for those. And yeah, I mean, a disclaimer about this presentation and about these numbers that you see here. So publishing a paper sometimes takes time. So the experiments that are reported in the paper are quite old compared to the current status of the PGX.D engine. So now PGX.D supports like a graphs with schema, and essentially leverage the schema in the runtime. It means lower memory, much better performance. We have done explicit like a PGQL, like a query execution improvement. So the numbers are much better now in the engine in general. And also we have added support for more physical constructs than simple graph patterns. And that's it from me. Thank you.
Thanks, Vasileios. Are there questions on this?
So I have one question. How do you shard the data among the machines?
So we don't do any specific, like a graph specific partitioning. So this is essentially a combination of random partitioning with edge balancing. And yes, pretty much that's it.
Okay, thanks. Other questions?
Yeah, can I?
Sure.
You could have fit all these graphs on a single big memory machine, I'd say. What made you choose to distribute it?
Yeah, so we used the scale factor 100 in the paper because it was pretty much impossible to evaluate the other engines with larger graphs. So we got this comment quite a lot by reviewers, and it's totally true, right? With PGX.D we can do much larger scales, but yeah, it was not realistic to get numbers from others.
So can you sketch how you prove that this, or how you make sure that this doesn't deadlock? Because I could imagine that for certain queries that naive approaches might have that.
Yeah, so essentially it's really like a network flow problem. So pretty much if you can send at least one message from every stage to another from any machine to the other, so if you guarantee that you have this, essentially for the last stage of the query, you can always complete locally because it always targets local vertices, right? So this means that you can always free up a buffer from the last stage of the query to the previous but last, which means that these states can always send a message, thus, essentially freeing one extra message that it can receive, and so on and so forth. So you can, I mean, there's at least one buffer flow from every stage to the next one, and then the last stage can always complete locally.
Okay. Well, if there are no other questions, then it's time to thank Vasileios.
Thank you.